Tonight, something almost impossible is happening above your head. The moon, the object that seems so steady, so permanent, so familiar, is leaving us. Very slowly, year by year, it is spiraling farther from Earth, and hidden inside that gentle drift is a story about gravity, motion, ancient violence, the slowing of our planet, and the strange fact that even the sky you grew up with is not fixed. This matters because the moon is not just decoration. It shapes Earth's tides, influences the length of our day, and has been part of the rhythm of this planet for billions of years. By the end of this, you are going to understand not only why the moon is drifting away, but how scientists know it, what that motion is doing to Earth right now, and why the answer reveals something much bigger about how the universe really works. And if you genuinely enjoy this kind of deep space storytelling, where strange cosmic facts turn into something you can actually picture and feel, take a second to like the video and subscribe. It really helps the channel, and it lets me keep making these long, immersive journeys into the universe. And in the comments, tell me where you are watching from, and answer this. If you could see the moon as it looked hundreds of millions of years ago, when it was much closer and larger in the sky, would you want to? Because that is exactly where this story begins. Picture Earth not as the calm blue world we know, but as a much younger planet, violent, molten, still assembling itself from debris in the early solar system. Somewhere in that deep past, the relationship between Earth and the moon was born in catastrophe. Why would the moon move away instead of falling in? How can gravity, the force that pulls things together, drive separation? If the moon is leaving, what does Earth lose as it goes? And how do human beings, standing on a small world under a bright night sky, know that this quiet retreat is even happening at all? At first glance, the whole thing sounds backwards. Gravity pulls. That is the rule we learn early, and it is true. Earth's gravity holds the moon in orbit. The moon's gravity pulls on Earth. So if gravity is an attractive force, why is the result not a steady inward collapse, but a slow outward migration? The answer begins with the simple but powerful idea. In space, falling and orbiting are deeply connected. The moon is always falling toward Earth, but it is also moving sideways fast enough to keep missing. That endless fall around a planet is what an orbit is. The moon is not hanging motionless in the sky like a lamp over a stage. It is in continuous motion, racing around Earth at about 1 kilometer per second, looping through space in a ceaseless balance between forward motion and gravitational pull. If nothing disturbed that balance, the orbit could remain stable for a very long time. But something does disturb it. The Earth itself is moving, spinning once every day, dragging its oceans with it, and deforming under the moon's gravity. That is where the real story lives. To understand why the moon drifts away, we have to start with the tides. Most people hear the word tides and think of shorelines, boats rising and falling, wet sand turning dry, and then wet again. But the real tide is larger and stranger than that. The moon's gravity does not pull equally on every part of Earth. The side of Earth facing the moon feels a slightly stronger pull than the center of Earth does. The far side feels a slightly weaker pull. That difference stretches the planet very slightly, creating two bulges, one on the side facing the moon and one on the opposite side. In the oceans, This stretching is easier to see because water can move more freely than rock, so the seas rise and fall. But Earth itself also flexes. The planet is not a perfectly rigid ball. It bends a little under gravitational forces, like a much stiffer version of a squeezed rubber sphere. The moon raises tides in the oceans and in the solid Earth. If Earth did not rotate, those tidal bulges would line up neatly with the moon, and one bulge would point almost directly toward it, the other directly away. But Earth does rotate, and it rotates faster than the moon orbits. This is the critical piece. Earth spins once in about 24 hours. The moon takes about 27.3 days to orbit Earth relative to the stars, and about 29.5 days to cycle through its phases as seen from Earth. So our planet is spinning much faster than the moon is moving around us. That means Earth is trying to carry the tidal bulges ahead of the line connecting Earth and the moon. Friction in the oceans, friction between water and seafloor, friction inside Earth's crust and mantle, all of it prevents the bulges from staying perfectly aligned. The bulges get dragged a little bit forward. That tiny offset changes everything. Now, the tidal bulge is not sitting directly under the moon. It is slightly ahead of it, and because that bulge contains mass, it exerts its own gravitational pull on the moon. Imagine the moon orbiting Earth, while Earth's tidal bulge runs a little ahead, as if our planet is trying to lead the dance. The bulge pulls on the moon, not straight inward, but a little forward along its orbit. That forward pull gives the moon energy, and in orbital mechanics, giving an orbiting object extra energy does not usually make it fall inward. It makes it move outward. The moon climbs to a higher orbit. Its distance from Earth increases. Its orbital speed actually decreases somewhat, because higher orbits around a planet are slower, but its total orbital energy increases. It is like a skater moving from an inner track to an outer one, covering a larger path more slowly. The system trades Earth's rotational energy for the moon's orbital energy. That is the heart of it. The moon is drifting away because Earth's spin is transferring energy and angular momentum to the moon through the tides, and Earth pays the price. As energy leaves Earth's rotation, our planet spins a little more slowly. The days grow longer. Not by enough for you to notice in daily life, but enough for geologists and astronomers to measure over long stretches of time. The moon gets farther away. Earth's spin slows down. Those two changes are linked parts of the same process, like opposite ends of a cosmic machine. This is where the story becomes both elegant and slightly unsettling, because it means the Earth-Moon system is not fixed. It is evolving, quietly, relentlessly. The familiar sky is not a permanent arrangement. It is a snapshot. So how fast is the moon receding? Today, on average, the moon moves away from Earth by about 3.8 centimeters per year. That is roughly the speed at which your fingernails grow. It sounds trivial, almost laughably small, but this is one of the universe's favorite tricks. Tiny changes, given enough time, become transformations. At 3.8 centimeters per year, over a human lifetime, the moon gets a few meters farther away. Over 1 million years, that becomes about 38 kilometers. Over 100 million years, thousands of kilometers. Over geological time, the difference becomes dramatic. The moon we see tonight is not the moon that shone over the dinosaurs, and certainly not the moon that orbited above the first oceans. But if that number is so small, how do we know it is real? Because during the Apollo missions, our astronauts left reflectors on the moon. Not cameras, not transmitters, reflectors. Special arrays designed to bounce light directly back to its source. Scientists on Earth can fire laser pulses at those reflectors and measure the time it takes for the light to return. Since light travels at a known speed, the round-trip travel time tells us the distance to the moon with extraordinary precision. It is one of the most beautiful measurements in science. A beam of light leaves Earth, crosses nearly 400,000 kilometers of space, strikes a man-made object sitting silently on the lunar surface, and comes back carrying a number. From that number, repeated over years and decades, we can watch the moon retreat. There is something almost poetic about that. Human beings went to the moon, left mirrors there, and those mirrors now help us measure a gradual planetary scale change in the architecture of the Earth-Moon system. It is not guesswork. It is not a rough estimate based only on theory. It is directly observed, and the theory behind it is even older. Long before laser ranging, scientists had already worked out that tides could transfer angular momentum. They knew that friction could make the tidal bulge run ahead of the moon, and that the gravitational interaction would affect the orbit. The laser data confirmed the broad picture with stunning clarity. The moon really is receding. Earth really is slowing. The mechanism really is tidal interaction. But to feel how profound this is, it helps to step back and see the system as a whole. Earth and moon are not separate actors merely passing near each other. They are locked together in a long-term exchange. The moon raises tides on Earth. Earth's rotation drags those tides ahead. The offset bulges pull on the moon. The moon moves outward. The moon also pulls back on the bulges, creating a torque that resists Earth's spin. So Earth slows down. It is a constant mutual reshaping, not through collision or explosive drama, but through persistent gravitational negotiation. If you could somehow speed up time and watch millions of years pass in seconds, coastlines would pulse, days would stretch, and the moon would spiral outward in a slow, widening dance. It would still orbit Earth, still shine by reflected sunlight, still cycle through phases. But the geometry would be changing. Little by little, the system would open. And this process is not unique to Earth and Moon, and tidal forces operate all over the universe. They heat moons, lock worlds into synchronous rotation, tear apart objects that wander too close to giant planets, and shape the long-term evolution of entire planetary systems. The drifting moon is one local example of a much broader cosmic rule. Gravity does not just pull. In systems with motion, spin, and internal friction, gravity can rearrange the architecture of worlds. To really appreciate that, we should go deeper into what tidal friction actually means, because it sounds almost too gentle for such large consequences. The tidal bulges in Earth's oceans are not smooth, perfect waves sliding frictionlessly around the planet. They interact with continents, shallow seas, ocean basins, seafloor ridges, and the shape of coastlines. Water sloshes, collides, and dissipates energy as heat. There are resonances, delays, turbulence, and regional differences. In some places, tides are small. In others, they are dramatic, surging through narrow channels or rising meters high. The exact details of Earth's tidal response are complicated, but the overall outcome is simple enough. Moving those bulges through real oceans on a rotating real planet wastes energy and creates the lag that lets the Moon gain orbital energy. Even the solid Earth contributes. The crust and mantle deform slightly under the Moon's pull, then relax. That internal flexing also dissipates energy. So when we talk about the tides, we are really talking about an entire planetary scale response to the Moon's gravity. Part oceanic, part rocky, part elegantly calculable, part messily physical, and all of it adds up to a steady transfer. Now, there is another strange twist hidden in this story. The Moon also raises tides on itself, and in the deep past, those tides mattered enormously. Right now, the Moon keeps nearly the same face turned toward Earth. We call that tidal locking. As the Moon orbits, it rotates once on its axis in exactly the same time it takes to go around Earth. That is why the same near side always faces us, while the far side remains permanently out of view from Earth's surface. This often confuses people because it feels like the Moon is not rotating at all, but it absolutely is. If it did not rotate once per orbit, we would see all sides over time. Its one turn per orbit rotation is precisely what keeps one hemisphere aimed at us. Why does it do that? Because long ago, the young Moon probably rotated faster. Earth's gravity raised tides inside the Moon and deforming it slightly. Those distortions created internal friction and drained rotational energy until the Moon settled into the lowest energy stable state, one rotation per orbit. Tidal forces first changed the Moon's spin. Then, in the Earth-Moon system we see today, tides on Earth continue changing the orbit. So the Moon is both a victim and a beneficiary of tidal evolution. It lost its free spin. It gained orbital distance. It became locked to Earth, even as it gradually moved away from it. This naturally leads to an even bigger question. If the Moon is receding now, was it once dramatically closer? Yes. Much closer. Not yesterday close. Not within the atmosphere. Not scraping the mountaintops. But in the early history of the Earth-Moon system, the Moon loomed much larger in the sky than it does now. The exact details depend on the stage of Earth's early evolution and on the complicated physics of tides through time. But the broad picture is clear. The Moon formed far nearer to Earth and has been moving outward for billions of years. To understand why, we have to visit the origin of the Moon itself, because this is not a side story. It is the foundation beneath everything. The leading explanation for the Moon's formation is called the giant impact hypothesis. Early in the solar system's history, when planets were still forming from collisions and mergers, a Mars-sized body, often called Theia, is thought to have struck the young Earth. This was not a glancing tap. It was a planetary-scale catastrophe. The impact would have blasted huge amounts of material into orbit around Earth. Over time, that debris gathered together and formed the Moon. There are details scientists still debate. The exact size of the impactor, the speed, the angle, how much material came from Earth and how much from Theia, how the chemistry of Earth and Moon became so similar. All of that is still an active area of research. But the general impact picture remains the strongest explanation we have. It accounts for the existence of a large Moon, for the Earth-Moon system's angular momentum, and for key features of lunar composition. Imagine the aftermath. Earth partly molten, glowing with residual heat, debris circling in a dense ring or disk. The early moon assembling from chaos, orbiting much closer than today. The tides on Earth would have been immense. The moon's gravitational pull scales strongly with distance, so bringing the moon closer does not just make a modest difference. It transforms the system. A closer moon means stronger tides. Stronger tides mean more efficient transfer of angular momentum. And that means the early outward migration may have been much faster than it is today. The process we now measure in centimeters per year may once have operated far more intensely, though the exact rates changed over time depending on Earth's oceans, interior, rotation speed, and the moon's distance. The young Earth almost certainly spun faster too. Days may have been much shorter, perhaps only a handful of hours long after the giant impact, though the specific numbers depend on the model and era. A faster spinning Earth would have dragged tidal bulges farther ahead, strengthening the torque on the moon. So, in its youth, the Earth-Moon system was far more dynamic than the calm modern sky suggests. This is one of the most fascinating things about astronomy. You look up at something ancient and stable-looking, and science reveals that it has a history, a real history. Not metaphorical, not abstract. Physical, violent, measurable, evolving. The moon has not always been where it is. Earth has not always rotated as it does. The length of a day has not always been 24 hours. The tides have not always behaved as they do now, and we can recover some of that history. One way scientists do this is by studying ancient rocks and fossils that record tidal cycles and day lengths. Certain sedimentary formations, built layer by layer under the influence of tides or seasonal patterns, and it can preserve clues to how often tides occurred and how many days there were in a year long ago. Some fossil organisms also laid down growth patterns that reflect daily and monthly rhythms. These records are not perfect, and interpreting them takes care, but together they tell an extraordinary story. Earth's day used to be shorter, and the moon used to be closer. For example, hundreds of millions of years ago, there were more days in a year than there are now. Not because Earth orbited the Sun faster, but because each day was shorter. The year's total duration stayed essentially the same on human timescales, set by Earth's orbit around the Sun, while the number of rotations Earth completed during that year was greater, more spins packed into the same trip around the Sun. That is exactly what we would expect if Earth's rotation has been gradually slowing down. That is a remarkable kind of evidence. It means the moon's recession is not just a modern measurement with lasers. It is written into the geological memory of Earth itself. Still, a natural question follows. If the moon is moving away by about 3.8 centimeters per year now, and it has existed for more than 4 billion years, could we simply run the clock backward and conclude that the moon must once have been absurdly close, or even inside Earth, on a naive straight-line calculation? Yes, and that is one reason this topic can become confusing. But the recession rate has not been constant. That is crucial. The current rate depends on the present shape of Earth's oceans, the arrangement of continents, the depth of seas, the planet's internal structure, and the exact dynamical state of the Earth-Moon system. In the distant past, all of those things were different. Continents shifted. Ocean basins opened and closed. The strength and pattern of tides changed. Earth's rotation changed. The moon's distance changed. So there has never been one single recession speed that you can extend backwards in a straight line forever. At some times in Earth's history, the tidal system may have been especially effective at transferring energy. At other times, less so. Think of pushing a swing. The effect depends on timing, angle, and the exact way the system responds. Earth's oceans have their own natural modes of sloshing, and when those interact with the forcing from the moon and the sun, the efficiency of dissipation changes. So the Earth-Moon relationship has not evolved at a perfectly steady pace, or it has changed rhythm as the planet itself changed shape. This matters because it reminds us that planetary science is rarely about one clean, simple number. The basic mechanism is elegant. The real world is more textured. Now let us return to something we often take for granted: the daily tides themselves. It is tempting to think of them as ordinary, earthly, weather-like cycles. But they are actually visible evidence of a gravitational conversation between worlds. Every tide that rises and falls is part of the reason the moon is not where it once was. Every shoreline, every estuary, every tidal current is participating in a billion-year exchange of energy and momentum. And it is not only the moon involved. The sun also raises tides on Earth. Solar tides are weaker than lunar tides, because although the sun is vastly more massive, it is much farther away, and tidal effects depend strongly on distance. The result is that the moon dominates Earth's tides, but the sun still matters. When the sun, moon, and Earth line up during new and full moon, their tidal forces combine to create stronger spring tides. When they sit at right angles during first and third quarter phases, the tides are weaker, called neap tides. That interplay does not drive the moon's recession in the same direct way the lunar tide does, but it affects the actual behavior of Earth's oceans, and therefore contributes to the messy details of tidal dissipation. Once again, the universe gives us a clear underlying principle wrapped inside real-world complexity. There is also a common misconception worth clearing up carefully. People sometimes hear that the moon is moving away and imagine it is escaping Earth, as if one day it will simply drift off into deep space and vanish. That is not how this works, at least not under the current long-term evolution of the system. The moon remains gravitationally bound to Earth. Its orbit gradually expands, but within the Earth-Moon system, there is a long road between receding and escaping. In fact, if no other factors interfered, and the system had enough time, Earth and Moon would eventually approach a kind of tidal end state. Earth's rotation would slow until one day was as long as the Moon's orbital period. At that point, Earth would keep the same face turned toward the Moon, just as the Moon already keeps the same face turned toward Earth. The two bodies would be mutually tidally locked. The Moon would hang over one hemisphere of Earth, nearly fixed in the sky, while the other hemisphere would never see it at all. That is a haunting image, a permanently hanging moon over part of Earth, absent from the rest. But in reality, the sun will intervene long before the Earth-Moon system reaches that final calm arrangement. Billions of years from now, the sun will evolve into a red giant, radically altering the inner solar system. So the ultimate textbook tidal endpoint is probably something Earth and Moon will never fully achieve in practice. Still, thinking about that endpoint helps clarify the direction of the process. The system is moving from faster rotation and closer orbit toward slower rotation and wider orbit, trending toward synchronization. Tidal friction is smoothing differences in motion. It is taking a system out of imbalance and nudging it toward a more settled state. That sounds serene, Drake, but the consequences across time are profound. Let us make them tangible. Imagine standing on Earth hundreds of millions of years ago. The moon would appear somewhat larger in the sky. Tides, depending on the era and the arrangement of land and sea, could be significantly different. The length of the day would be shorter. Sunset would come sooner. Dawn would return sooner. The entire rhythm of life on Earth would be paced by a faster spinning planet and a closer lunar companion. Now go back much farther, into the deep Archean, or the aftermath of the moon's formation, and the picture becomes more extreme. The moon could dominate the sky far more dramatically. Tidal forces could be enormous. Earth's surface environment, especially coastal and shallow marine environments, would be shaped by a much stronger lunar influence. Some scientists have even explored how these stronger tides may have affected the chemistry and cycles of early Earth, though one must be careful not to overstate such links. The details are still debated, but there is no doubt that a closer moon meant a more forcefully coupled Earth-Moon system. Then bring the clock forward to now. The moon is still important, still powerful enough to move whole oceans, still visually dominant in the night sky. But it is already much farther away than it was in its youth, and if you leap forward into the distant future, it will appear smaller still. This leads to one of the most quietly surprising consequences of lunar recession. Total solar eclipses will not last forever. Right now, we live in a rather special era. The sun is about 400 times wider than the moon, but also about 400 times farther away, which makes them appear almost the same size in the sky. That is why the moon can sometimes cover the sun so precisely during a total solar eclipse, turning day into an eerie twilight and revealing the sun's outer atmosphere, the corona, as a ghostly white crown. But the moon is moving away, very slowly, yes, but steadily. As it recedes, its apparent size in our sky shrinks. Over immense timescales, that means it will no longer be large enough to fully cover the sun. Total solar eclipses will eventually disappear, replaced by annular eclipses in which the moon passes in front of the sun, but leaves a ring of sunlight visible around its edges. That is one of those facts that changes how you feel about the present moment. Total eclipses are not just beautiful. They are time-limited. We happen to live during an era when the geometry still works. The sky we inherited includes a coincidence that is both scientifically explainable and emotionally astonishing. And even that coincidence has an expiration date. The moon's retreat changes the look of the sky itself, and yet although the process is real and measurable, it does not pose any danger on human timescales. The moon is not suddenly pulling away in some dramatic event. You will not notice it from one year to the next by looking. The tides will continue. The phases will continue. Moonrise and moonset will continue. The changes matter over millions and billions of years, not Tuesday afternoon. Astronomy often works like this. It teaches you to think in layers of time. human life unfolds in years and decades. Civilizations in centuries and millennia. Geology in millions of years. Planetary evolution in billions. The moon's recession belongs to that deeper tempo. To understand it is to stretch your sense of time until the familiar world starts to feel dynamic in a new way. There is also the question of whether the recession rate could ever reverse. Could the moon start moving inward instead? In the current Earth-Moon configuration, with Earth rotating faster than the moon orbits, the torque from the tidal bulge transfers angular momentum outward, so the moon recedes. If Earth were spinning more slowly than the moon orbited, the situation would be different. The tidal bulge would lag in a way that could pull the orbit inward instead. In other systems, this does happen. Some moons in the solar system are spiraling inward toward their planets. Mars gives us a dramatic example with its moon Phobos. Phobos orbits so close to Mars and so quickly that it circles the planet faster than Mars rotates beneath it. Because of that, tidal interactions are causing Phobos to slowly spiral inward. One day, it may break apart under tidal forces or crash into Mars. So tidal evolution can go in either direction, depending on the relative speeds of spin and orbit. That comparison helps reveal just how specific the Earth-Moon story is. Our moon moves outward because Earth spins faster than the moon circles us. Change that relation, and the direction of evolution changes too. Tides can be creators of stability or agents of destruction. They can lock moons, heat interiors, widen orbits, shrink orbits, and in extreme cases, tear worlds apart. Jupiter's moon, Io, for example, is the most volcanically active body in the solar system, largely because tidal flexing from Jupiter and orbital resonances with other moons need its interior, generating immense heat. Saturn's moon, Enceladus, sprays water vapor and ice from a global ocean beneath its icy crust, with tidal heating playing a major role there too. Tidal forces are not a side detail in celestial mechanics. They are among the major sculptors of planetary systems. And the Earth-Moon system is special partly because we can feel those forces directly. We live on the world being deformed. We can watch the sea rise under the pull of another body. We can stand at the edge of an ocean and literally see the visible expression of orbital physics. That is worth lingering on. So much of astronomy feels remote. Exoplanets are light years away. Black holes lurk in abstract equations and distant galaxies. Even the planets of our own solar system are usually points of light or robotic destinations. But tides are astronomy made physical under your feet. The moon is not just up there. It is pulling on Earth right now. It is moving water in harbors, straits, and bays. It is stretching rock. It is slowing the spin of the world. And through that ongoing interaction, it is inching away. There is a beautiful severity to that. Not violent, not sudden, but absolute. Now, the phrase "the moon is moving away" can create another subtle misunderstanding. Away from what point exactly? The moon does not orbit the exact center of Earth in a perfect static sense. Earth and moon both orbit their common center of mass, called the barycenter. Because Earth is much more massive, that barycenter lies inside Earth, but not exactly at its center. So, in a technical sense, both Earth and Moon are circling around a shared balance point. This does not change the main story, but it refines it. The Earth-Moon system is a two-body dance, not a simple one-way arrangement, where a tiny satellite circles a perfectly fixed planet. Earth wobbles slightly as the Moon moves around it. This wobble is part of why the Moon's gravitational influence is so physically real to our planet. And when angular momentum is transferred, it is the dynamics of this whole system that evolve. Angular momentum is one of those terms that can sound intimidating, but the basic idea is straightforward. It is the oomph of rotational motion, the tendency of something moving in a circle or spinning to keep doing so. In an isolated system, a total angular momentum is conserved. It can be redistributed, but not simply disappear. In the Earth-Moon system, some of Earth's rotational angular momentum is being transferred to the Moon's orbital angular momentum. Earth spins more slowly. The Moon moves to a larger orbit. The total budget balances. That conservation is what makes the story so satisfying. The Moon is not mysteriously stealing distance. There is an accounting, a physical exchange. The slowing of Earth and the recession of the Moon are mathematically and conceptually bound together. And this also means there is a faint but real sense in which the Moon's retreat is powered by Earth's spin. The energy source is our planet's rotational energy, bled away through tidal dissipation. The Earth is like a spinning top, gradually losing some of its spin. Not some, and the Moon is using part of that lost rotational order to lift itself into a wider orbit. If you want a more intuitive analogy, imagine a rotating platform with a weight connected in such a way that friction and torque slowly transfer motion outward. The details are different, but the spirit is similar. A spinning system can do work on an orbiting one. The reason it feels unintuitive is that in everyday life, we rarely think about the oceans as giant moving handles that gravity can grab. But that is what they are, in effect. Vast masses of water displaced by the Moon, carried by Earth's rotation, then pulling back gravitationally on the Moon in return. Of course, no analogy should be pushed too far. The Earth-Moon system is not a machine built by human hands. It is a self-organizing gravitational system operating through differential forces, fluid dynamics, and long-term orbital mechanics. Still, the analogy helps because it turns an abstract orbital shift into a transfer process you can imagine. Now let us ask something more philosophical, but still scientific. Would Earth be the same world without this particular Moon, at this particular distance, with this particular history? Not even close. The Moon affects Earth in many ways beyond the everyday tides. It stabilizes Earth's axial tilt to a significant degree, helping reduce wild long-term variations in the angle between Earth's spin axis and its orbit around the Sun. That matters because the tilt influences climate patterns and seasons. Without a large Moon, Earth's obliquity might vary much more chaotically over geological timescales, potentially leading to more extreme climate shifts. Scientists study these questions carefully, and the exact magnitude of the Moon's stabilizing role involves complex dynamics, but the broad conclusion is solid. The Moon has been an important partner in Earth's long-term behavior as a habitable planet. That does not mean the Moon made life inevitable, or that Earth would have become uninhabitable without it. Those would be overstatements. Life is resilient, and planetary evolution is complex. But it does mean the Moon is not an incidental companion. It is woven into Earth's story, and that makes the recession feel more poignant. The moon is leaving, but not like a traveler walking out the door, more like a lifelong dance partner taking one tiny step back every year, slowly changing the rhythm of the room. From a scientific perspective, this is also a masterclass in how we know things we cannot witness directly over full time scales. No human being has watched the moon move noticeably farther away with their own eyes. No civilization has tracked the full billion-year arc of the Earth-Moon system. And yet we know it is happening because the evidence comes from multiple directions at once. We have direct modern measurement from lunar laser ranging. We have physical theory from gravity, orbital mechanics, and tidal dissipation. We have geological clues showing shorter ancient days and a closer moon in the past. We have computer models that simulate the system's evolution. We have comparisons with other moons and planets. The power of science here is not one dramatic observation. It is convergence. Different methods, different time scales, different lines of reasoning, all pointing to the same deep answer. That is often how the most reliable scientific knowledge works. Not one miracle fact, but a network of mutually reinforcing evidence. And yet the answer remains beautifully strange. Because when you strip away the equations and measurements, the core revelation is almost dreamlike. The seas are stealing spin from the Earth and giving it to the moon. That is the kind of sentence that sounds mythic until you realize it is physics. The next layer down is even more interesting. Because the moon is moving away does not mean the path is a perfect, simple spiral in a flat diagram. The real orbit is elliptical, perturbed by the sun, affected by Earth's equatorial bulge, and measured relative to a moving Earth that itself orbits the sun. Celestial mechanics is full of these layered motions. We simplify them to grasp the main mechanism, but the actual dance is richer. The moon's distance changes over the course of each orbit too, since its orbit is not a perfect circle. At perigee, it is closer. At apogee, it is farther. The long-term recession is an average trend laid over all of that short-term orbital complexity. This is another place where astronomy rewards patience. Reality is not less beautiful because it is complicated. It is more beautiful. You begin with a childlike picture. Earth here, moon there. Then you learn about orbits, then tides, then torques, then angular momentum, then geological evidence, then barycenters and long-term climate influence. The more closely you look, the less simple the sky becomes, and the more coherent it becomes too. The universe is not random chaos. It is intricate and lawful at the same time. We can also appreciate how extraordinary our observational position is. We are the first species on Earth, as far as we know, capable of understanding that the tides are linked to the moon's orbit, that the moon came from a giant impact, that its distance can be measured with lasers, that the day lengthens because rotational energy is being dissipated through the oceans. For most of human history, the moon was a symbol, a calendar, a deity, a mystery, a guide to time and agriculture and ritual. It still carries all that emotional weight. But now we can add something else, mechanistic understanding without loss of wonder. If anything, the wonder deepens. Because this is not a case where science drains the magic from the night sky. It does the opposite. It reveals that the apparently serene moon is part of a dynamical system so subtle and vast that it takes geology, astronomy, mathematics, and space exploration to fully grasp. The more true the story becomes, the more astonishing it is. Now imagine standing under a full moon with all of this in mind. Its light is reflected sunlight, crossing space in about 1.25 seconds. Its face is tidally locked, showing the same scarred hemisphere that ancient humans saw. Its orbit is widening because Earth's rotating oceans are handing it energy. The day beneath your feet is microscopically longer than it once was. The eclipse geometry of our age is temporary. The moon itself may have been born in a world-shattering impact, and every tide at every coast is a visible reminder that nothing in the cosmos stays truly still. That is not a poetic exaggeration. It is the plain scientific truth. There is another subtle consequence of Earth's slowing rotation worth touching on, because our timekeeping systems are partly built around Earth's rotation. Tiny irregularities and long-term slowing can matter in precision timekeeping. This is why leap seconds have occasionally been added to coordinated universal time, not because of the moon alone in a simple direct way, but because Earth's rotation is not perfectly constant, and tidal breaking is one of the long-term influences. Human technology, satellites, communication systems, and precise clocks end up brushing against the consequences of lunar tides. The moon's retreat is not only a geological or astronomical curiosity. It reaches all the way into the structure of modern civilization's timekeeping. Even in this, the familiar and the cosmic overlap. And then there is the emotional side of scale. We often think change must be visible to be real, but astronomy teaches another lesson. Some of the most powerful transformations in the universe happen too slowly for a single life to feel. Continents drift, stars evolve, galaxies collide over eons, planets cool, orbits widen. In human terms, these things seem fixed. In cosmic terms, they are processes. The moon's recession is a perfect example of that hidden motion. Every month, the moon looks familiar. Every year, the same phases return. Generations write poems under it and imagine it unchanging. Yet beneath that apparent permanence, the system is quietly unfolding according to laws older than life on Earth. That tension between permanence and change is one of the deepest themes in astronomy. The sky feels eternal because our lives are short. Science lengthens our view. It gives us access to histories and futures no one can directly witness in full. Suddenly, the eternal becomes dynamic. The static becomes historical. The ordinary becomes epic. And still, we should remain honest about what is uncertain. Scientists are highly confident about the basic mechanism of tidal recession. That is established. The current rate, the slowing of Earth's rotation, the existence of the torque, the reality of tidal dissipation, all of that is secure. But when we go far back into the early Earth-Moon system, the details become less certain. Exactly how fast the moon moved outward at different times, how Earth's oceans and atmosphere influenced the process, when specific resonances or transitions occurred, how the post-impact Earth behaved. These are active research topics. Models improve. New geological evidence appears. The broad story is known, the fine print is still being refined. That distinction matters because good science is not fragile when it admits uncertainty. It is stronger. We know the moon is receding. We know why in the essential sense. But planetary history is complex enough that some chapters remain partly blurred. There is dignity in saying both things at once. In fact, that is part of what makes the topic so alive. The moon is familiar enough to feel ancient and settled, yet rich enough to still contain unresolved questions. Even our nearest celestial neighbor is not fully exhausted as a subject of discovery. If you want one more way to feel the scale of this process, consider the average Earth-Moon distance today, about 384,400 kilometers. Light takes about 1.28 seconds to travel that gap. The moon is far enough that all the Apollo missions, all our laser experiments, all the lunar dreams of human culture take place across a gulf that is both nearby in cosmic terms and immense in human terms. And even across that gulf, gravitational interaction is strong enough to move oceans and alter planetary rotation. It is hard not to be impressed by gravity after that. No beams, no contact, no sound, just mass shaping motion across space, persistently, invisibly, over unimaginable time. That persistence is the true drama of the moon's retreat. Not speed, but patience. A comet can blaze, an asteroid can strike, a supernova can erupt. Those are spectacular forms of change. But the widening of the moon's orbit belongs to a different class of cosmic event. It is the kind of change that rewrites a world not through shock, but through endurance. Or it says that if a force is lawful and continuous, it can transform planets with nothing more than time. That may be the most universal lesson in the whole story. When we look beyond Earth, we see tidal physics everywhere. Exoplanets huddled close to red dwarf stars are often expected to become tidally locked, with permanent day on one side and permanent night on the other. Giant planets may host moons whose interiors are heated by tidal flexing enough to maintain subsurface oceans. Binary star systems exchange angular momentum. Compact objects spiral together through other mechanisms and interactions. The specific details differ, but the same underlying truth returns. Motion, gravity, and time are enough to build worlds, change worlds, and sometimes unmake them. So the moon drifting away from Earth is not an isolated curiosity. It is a local window into a universal process. By understanding this one nearest example, we understand something about how the cosmos behaves at every scale. And perhaps that is why the story feels so satisfying. It begins with a familiar object and ends with a cosmic principle. It starts with moonlight on water and opens into the mechanics of planetary evolution. The wider meaning of all this is not simply that the moon is getting farther away. It is that even the most familiar parts of our world are part of long, hidden processes that only reveal themselves when we learn to think in deeper time. The moon seems timeless because human life is brief. But the universe is not built for our timescale. It is built in gradual exchanges, slow transformations, and relationships that unfold across billions of years. There is something humbling in that, and also something deeply beautiful. Earth is not an isolated stage with a fixed backdrop. It is a participant in a living celestial system. The tides, the length of the day, the face of the night sky, even the possibility of total eclipses, all of these are connected. To understand why the moon drifts away is to realize that the border between Earth science and space science is thinner than it looks. The ocean on a shoreline and the orbit of a moon are chapters of the same story. And perhaps the most awe-inspiring part is this. We are a species small enough to be moved by moonlight, yet capable of discovering that moonlight belongs to a billion-year transfer of energy between a spinning planet and its companion. We can stand on a beach, watch the tide come in, and know that we are witnessing not just water moving, but the visible trace of a cosmic transaction that has been reshaping Earth since before complex life existed. That is what science at its best gives us. Not colder facts, but a larger reality. So the next time the moon rises and looks calm, bright, and permanent, remember what is really happening. It is drifting away from Earth, centimeter by centimeter, while slowing the spin of the world beneath you, changing the future of eclipses, and preserving in its quiet orbit the memory of an ancient planetary collision. Thank you for being here. And if this journey gave the night sky a little more depth, I am glad we shared it.